Welcome, CHEM200. You have made it to the last lecture. Congratulations. The end is near, people. We are getting close. A couple of reminders. You have a lot of homework out there. Remember, Chapter 9 is the big one, but you still have 2 more assignments. These last 2 chapters, we just do a little bit from Chapter 12, so they're combined in one homework assignment. Please see me during office hours if you want to go over any kind of homework questions, or you have grade or comment questions from exam. You got 1 quiz remaining and 1 regular lecture exam. So that review sheet is posted. Like I said, the end is in sight, so I encourage you, finish strong. If you take a look at the schedule, we've got the last lecture, last quiz, last lecture exam. And if you look at the way the schedule wraps up, that's nice because then you have a weekend, rest, recover, and then you come back and you have a holiday on Monday, and then the 27th, you can focus 100% on getting ready for the final exam. So this review, I'm counting that as activities 4 and 5. I am bribing you. I'm giving you 10 points to review for the final exam. So I'll have a practice exam available for you to do. Come to office hours. You can go over that. Work through those problems. Then you have a weekend, and then the final exam the next week on Monday, and I'll give you more information about that in a future video. So this is it. This is the topics. I want you to know that this topic, intermolecular forces in particular, is usually a very important topic for organic chemistry. The classes that I previously would teach, this would be the focus, and then organic chemistry concepts would build around that. Here, I know it's the very last chapter, the very end of the semester. It's hard to kind of get geared up for 1 more of these, but these are some really important topics that I'm going to cover, and it's going to go on in more chemistry if you continue. So, like I said, we're combining chapters 11 and 12 in this 1 video. Intermolecular forces is going to be the focus, but then we'll add this piece on the solids at the end, and we'll work in some other states of matter and properties in that. So let's revisit these properties. Again, these are things you've been seeing from Chem 152 to Chem 200 early days. This you probably could fill out before we even started talking. This is states of matter, gas, liquid, solid. What about their density, their shape, their volume, and so on. What we're talking about today, though, is the intermolecular forces. So again, really want to emphasize, if particles are packed very closely together to form a solid, you can imagine they have strong attraction to each other. And we did gases not too long ago. The whole idea of gases, they're empty space. There's no interaction. So this is a very weak intermolecular force. So we'll go in great detail what intermolecular forces are and how that helps understand states of matter. So in general, when we talk about solids, we probably think about these crystalline solids, which are regular, ordered, and that's a repeating pattern over and over again. We looked at lattice energy, so the lattice was the repeating ions over and over. But there are amorphous solids that don't have a pattern. But this is what we're focusing on in this chapter, and at the end of the chapter, I'll talk more about some different types of solids. So changes of state. We, again, have talked about solids, liquids, and gases. The transition, melting, evaporating, maybe condensing, depositing, sublimation. These are all words that maybe you've seen before. And temperature is a way to change those states. But also I want you to see here, pressure, that was our gas chapter, also is a way to change those states. I'm going from gas to a liquid. So compressing it, changing the pressure. So these are ways to get in between. And if you look again, if we're thinking about the forces between atoms, okay, you can see why this has a greater intermolecular force on the left for solids, and on the right, there's very weak intermolecular forces. So let's get to this. The theme of the book Again, if we were on campus, you probably would have been hearing me say this over and over again. Structure determines properties. That's the theme of the book. So if you understand the structure, then you can get to the properties. Well, if you take a look at these examples here, ethanol, dimethyl ether, the mass, exact same. Okay, that's because the molecular formulas are the exact same. The structure, and it's got the structural formula here, that's what affects the properties. Remember, the structure, in this case, how are the bonds arranged, and what intermolecular forces connect those molecules, and the property that we're looking at is boiling point. Look how significantly different, 100 degrees difference in boiling point because of the way the atoms are arranged. So we're going to come back to this and see why this is so high and why it's so significant. But I just want to give you a little backbone of the structure. And you can see that's carbon, carbon, oxygen, hydrogen. And then the hydrogens all fill out on these carbons. This is organic molecule. So what we saw as well, carbon has 4 bonds. That could be single, double, triple bonds. Here they're all single bonds. And this is how it's arranged. Okay, so this is actually an organic compound, as I mentioned, and it's called an alcohol. There's an OH group here. Well, this is an organic compound. Again, it looks exactly the same. It should be the same. Why are the properties different? Because the structures are different. So if we look here, the CH3 still looks together. It looks the same. But now the oxygen's in between here. And this is an ether, organic functional group. And we can see that looks different than the alcohol above. Okay, so what we're going to see is the way this alcohol interacts with another molecule of ethanol leads to a high boiling point. The way this ether interacts with another ether leads to this low boiling point. So this is intermolecular forces. All right, so we've been saying that word a lot. What does it mean? It's the interaction between charges, partial charges, or temporary charges. Let me be really clear on that. This is a molecule, and we're talking about how it interacts with another molecule. Okay, so that's these dots here. That's intermolecular forces. Most of our chemistry has been talking about a molecule and its bonds. Is it an ionic bond? Is it a covalent bond? So this is intramolecular forces, but now this focus is on inter. So we're thinking about multiple molecules, how they interact. So you can see intra is shorter, and as we've seen before, that's going to be stronger. But what we're talking about, inter, is longer, but still has a significant effect. So what we need to think about then is our molecules or our ions, whatever it is, does it have a full charge? Does it have a partial charge? Is the charge temporary? Okay, these are the things that we're looking at here in describing intermolecular forces. The first force that we're going to look at is the weakest. And as I mentioned, if it's intermolecular force, it's weaker than bonding forces. So ionic bond, covalent bond, that's strong. What we're talking about, intermolecular forces, and those are weak. So the first one is called dispersion forces, or London. You may see London dispersion forces, and this is present in everything. Okay, so all molecules, atoms have this, and the way it's described is it's an instantaneous dipole or temporary. Okay, so let's revisit what we've learned about electrons. Of course, electrons are in orbitals. We can't predict exactly where they're at. We think they're in this region, but they don't follow a pattern. And look, these two electrons could have actually ended up way to the left. Random, way to the left. Well, then you can see that builds up a partial negative. Well, now we have this whole void over here of no electrons. That builds up a partial positive. Then you can see the instantaneous part is that these two then are attracted to the positive. Now another void, positive, these two, the partial negative. So this is a partial positive, partial negative that's induced. It does that with its neighbors. So this is temporary. Okay, these are atoms, no unequal sharing. This isn't a dipole moment. This is a temporary dipole based on the nature of electrons. So it's a very weak force. It exists. We know it exists because things like the noble gases, you can see noble gases have a boiling point. That means it goes from the liquid to the gas. So if it's in the liquid state, it's got some attraction. Those particles are very close together, so there's got to be some attraction. So what I want you to see here is that, of course, size is increasing as we go down the periodic table. That means the mass is increasing, and now we can see the boiling point is increasing. And what determines properties? The structure and those forces between them, and in this case, dispersion force increases with the increasing size. So it's harder to separate the liquid into a gas, 165 Kelvin, because there's greater mass, it has greater dispersion force. Another way to look at it is these organic molecules over here. Remember, we're thinking about many of these molecules together. So in this case, pentane, you can draw in this line structure formation. So that's 1, 2, 3, 4. That's 5 carbons in a line. And if we're thinking about many of these, look how these can pack in nice and closely. Okay, so this structure allows the molecules to get close, and attraction, stronger intermolecular force, stronger dispersion force. So look at the boiling point, 36.1. Under here, neopentane, it has the same molecular mass, it's the same number of carbons. So I'll put a carbon in the middle, and I'll have some carbons coming off. But you can see that's harder for that to get close together. It's all spread out. It makes it difficult to really get in and have this strong attraction to form a liquid. So you can see its boiling point is much lower. So the particles don't want to interact as much. That has a lower boiling point. Here they want to interact more. It has a higher boiling point. The next intermolecular force, so that was number 1, dispersion, the weakest. Now we get to number 2, dipole. So if you remember, if we talk about a dipole, that's a polar molecule. So there's a permanent partial positive, partial negative. So if you look down here, again, organic molecules showing there's a partial positive where the carbon was, because it has a lower electronegativity, partial negative where the oxygen, and then of course it just lines up with the molecules around it in that fashion where there's this intermolecular force and attraction. So this is a permanent dipole. Okay, so we looked at dipole moments, and we actually saw the measurement, just a couple of slides on measurement of dipole moments. So that's what I'm showing here, is this dipole moment shows the measurement. It can range from a very non-polar like 0.08 to very polar 3.92. And as you can imagine then, if it's a greater dipole moment, it's more polar, it has greater dipole-dipole interaction, so it has a much higher boiling point than this propane, which has a very low intermolecular forces. It really only has dispersion forces. So boiling points increase with increasing the dipole moment. So that's 2 of our intermolecular forces. The third, this one's so annoying, sorry. Remember, these are forces. These are intermolecular forces. So I'm crossing this out. I know that's the name of it, hydrogen bonding. But look, it's interaction between molecules. It's not a bond, an ionic bond or a covalent bond. It is a force between molecules. So this one is very important to be aware of, that it's very specific. the hydrogen has to be bonded to fluorine, oxygen, or nitrogen. And really, this is just called a super dipole-dipole or a special dipole-dipole. And the reason it's so special is because we know fluorine's the most electronegative. So of course that gets the partial negative. Hydrogen gets the partial positive. But now we're thinking about the neighboring molecule. So the reason why it's special is because hydrogen and fluorine are very small atoms, and this electronegativity difference is so strong that this attraction between these molecules is really, really strong. Okay, so that's the effect of a small hydrogen atom and then these other electronegative atoms that are really electronegative, and then they're also small. Well, why is this a big deal? Well, if you take a look here, you got a nice linear pattern. And if you continue in group 4A, that's tin, germanium, silicon, methane even drops off in the boiling point. And here, group 6A, look how water shoots up to 100. The reason water, such a small molecule, has such a high boiling point is the hydrogen bonding that can take place. So there's 2 hydrogen bonds for one water molecule here. So this is significant, really important chemistry, the hydrogen bonding intermolecular force. So all of these forces, so that's dispersion, dipole-dipole, hydrogen bonding, are talking about pure substances. I did water with water. That's a pure substance. Okay. This last intermolecular force, even the name gives it away. It involves an ion, and it involves something with a dipole. Okay. So of course, the ion is the ionic compound. The dipole we've already talked about are polar compounds, and you looked at this when we went to solutions. You said all the partial positives in water line up and surround the fully negative charge of the anion. All the partial negatives surround the cation of the ionic compound. So to conclude, what we've done here with these intermolecular forces is summarized what's going on between molecules or between atoms. So dispersion is the weakest, so we're going in strength here. And then we went to dipole-dipole. So remember, this is a temporary dipole or temporary partial charges, temporary dipole for dispersion, permanent dipole for dipole-dipole, permanent dipole for hydrogen bonding, but it's special case, small, and it's a very big dipole. And then lastly, the strongest, full charge and a partial charge. So these are the intermolecular forces that exist. So here's how this would look. Choose the substance that is a liquid at room temperature. Okay, the other is a gas. So one of these is a liquid, one is a gas, and it has everything to do with intermolecular forces. So you can pause it, take a look, see what you think. Mainly, I would encourage you to think about the structure. So in this case, we would have to draw the Lewis structures, and we think about what our central atoms are. Of course, hydrogen are terminal, so they go on the outside. And if you take a look here, there's lots of hydrogen atoms. So the temptation is, if there's a hydrogen, it's hydrogen bonding. But what was the rule? It's a very specific rule. The hydrogen has to be bonded directly to the fluorine or directly to the oxygen or nitrogen. So it's not bonded to that. Okay. Here, on the other hand, hydrogen is bonded directly to the oxygen. That's an alcohol group that we saw earlier. The OH, and then the carbon is coming off the other end, and the hydrogens are coming off that. So now we can see that the molecule on the left has hydrogen bonding. So that's the strongest out of the pure substance forces. And this only has dipole-dipole because of this carbon fluorine. So this is a lot of review of previous chemistry. What are covalent bonds? What are polar covalent? What are nonpolar? So that's previous chapters, previous exams, and now it's applying it to intermolecular forces. So we're still going to continue with this idea of intermolecular forces, but now it's more of how these forces are overcome. Okay, so vaporizing something, vaporization goes from the liquid to the gas, and of course this happens with heat. You can heat this up so the molecules moving around, it separates faster, it goes into the gas phase. If you spread out this liquid, a puddle on the street, that's going to have a greater rate of evaporating the water. The intermolecular forces. So if it has weak intermolecular forces, then it vaporizes easier. If it has really strong intermolecular forces, it wants to stick together. It wants to stick in this liquid phase. It does not want to go into the gas phase. So this is how the intermolecular forces compare. A couple things now on if we vaporize, so go from liquid to gas, or if we condense, go from gas to liquid. Look at this. This is chapter 9 topics, endothermic. So evaporating always takes heat. Okay? To change the liquid to a gas, it takes heat. To go from a gas to a liquid, it releases heat, because those are opposite reactions. So we saw that in Hess's law. You flipped the reaction, you flipped the sign. So that's endothermic, exothermic. So the enthalpy of vaporization, so again that goes back to chapter 9, delta H. The definition is the amount of heat required to vaporize 1 mole of liquid to gas. Okay? We just said if it's vaporizing it, that is endothermic, so it's a positive sign. So if we take a look here at water, and we see the enthalpy of vaporization at 25 degrees, that's 44, and look at the units, kilojoule per mole. So we'll come back to a calculation with this, so we'll use this later, but it varies for substances, and you can see the different values here, and that's based on what the molecule is, intermolecular force, and so on. So vapor pressure you've actually used in Chem 152 lab, the water vapor pressure. You've seen some of these in gas law questions, but maybe we haven't ever really given a good definition. It's the pressure of a gas that's in equilibrium with its liquid. So there's a liquid, and then the gas is above the liquid, and then this equilibrium, see these arrows, the rate of the liquid molecules going to the gas and the rate of the gas molecules going to the liquid is equal. So that's equilibrium. That's the vapor pressure. And again, just like we said with evaporation or vaporizing, if there's strong intermolecular forces, these want to, the particles want to stay together, and you'd have a low vapor pressure. If you have very weak intermolecular forces, then you'd have a much higher vapor pressure here. And that's what this plot is here. We can see vapor pressure versus temperature. And you can look at the different substances. Okay, so remember we said water has hydrogen bonding. That means the liquid wants to stay together. So you can see this curve is much farther down. Diethyl ether, we talked about that ether earlier, that has that low boiling point. So you can see this curve is much farther to the left. So what would you say about ethylene glycol then? Okay, it has even stronger intermolecular forces than water. There's multiple OHs to have hydrogen bonding. So then you can see the vapor pressure is very low, and the vapor pressure of ethanol is in between water and diethyl ether. So the boiling point then is the temperature at which vapor pressure equals the external pressure. So we've used boiling points, the reference points for temperature. So just wanted you to see this table, the approximate boiling points. It depends on elevation. Okay, so you can see a variety of these. Typically we associate the boiling point of water at 100 degrees Celsius. That's the normal boiling point. the temperature at which vapor pressure equals 1 atmosphere. So that's the pressure at sea level here, 1 atmosphere. So there's a relationship, mathematical relationship I just wanted you to see. You can see the vapor pressure, natural log of vapor pressure, versus 1 over the temperature. So that's your x variable. This is your y variable. You can solve this and get the enthalpy of vaporization. So that's delta H there of the vaporization. So we're looking at phase changes. Does it go from a liquid to a gas? Does it go from a gas to a liquid? And the things that are involved in that. So the next one then is, maybe you've seen this terminology, maybe you haven't, but sublimation deposition. This is when the solid, sublimation, goes directly to the gas. Okay, so that's sublimation. Maybe you've seen this with dry ice, so you can get dry ice at the grocery store. Halloween, you pull out this solid and it turns into this gas, and there's not a puddle, there's no liquid around. So that's sublimation. Deposition is the opposite. Continue with these phase changes. The fusion isn't just another way to say melting, so that's solid to liquid. Of course, that's endothermic, because we think about a piece of ice, you got to heat it up to go from the solid to the liquid. And this, I think, is a little harder to think about, but just flip the sign. Remember, flip the equation. If we think about water, solid, I think that's much easier to look at water solid and say, oh yeah, I definitely need to heat that up to get to water liquid. Well, if I need to heat it up, that means it's endothermic. Well then, if we're looking at freezing, it's the opposite. So that's the flip. So you flip the sign then, and that would make it exothermic. So that is one way to look at it. Whoop, that should be a solid there. Sorry about that. So enthalpy of fusion, just like enthalpy of vaporization, we look over here. For water, it's 6.02 kilojoules per mole. So that's the amount of heat required to melt 1 mole of a solid into the liquid. Again, phase change, if we're going from particles that are very compact to spreading out the particles, that takes heat, so that's always endothermic. So what we've just put together then is a way to look at a heating curve. Okay, so what I've got here is the temperature change on the y-axis, and on the x-axis is the heat being added. And if you take a look, I want to point out several regions. Okay, so if you warm up ice, I know that sounds kind of strange. We kind of think of maybe ice as the same temperature, but you can have different temperatures of ice. So if you warm up ice, that's a change in temperature from -25 to 0. And then what happens? Well, ice melts. Okay, so you can see when something changes states, changes phases, there's not a temperature change, but there is heat being used, right? So this heat is being used to separate the particles from very close together to spread out. And then we go back to a temperature change. So the liquid now is being changed in temperature, and you get to 100 degrees Celsius. And then, of course, you, at 100 degrees, change the state again. So that's vaporizing it. And lastly, then steam can actually change temperature as well. So you've got 5 different things going on here, but really you've got 2 calculations. Okay, so how did we calculate the heat of a substance at different temperatures? Okay, so that's step 1. You've seen that. That's Q equals mc delta T. So you got to know the mass, and the specific heat is different for solid water versus liquid water versus gaseous water. So you have to use the right specific heat, but it's a Q equals mc delta T problem. So that's a Q equals mc delta T problem. That's a Q equals mc delta T problem. And that's a Q equals MC delta T problem. So that's 3 Q equals MC delta T problems. So you've done those, you've seen those. You just have to use the right C and the right delta T's. 4 is what we just talked about, and that's when we have a constant. The vaporization constant is in kilojoules per mole, but we just want the kilojoules. That's what we're looking for. So we just have to multiply it by the moles. So that's the kilojoules per mole for vaporizing. That's a constant. You'd be given that. And over here, remember another phase change. This is the constant for melting. That's another calculation. So let's put all this together. The problem I will assign is how much heat is needed to raise the temperature of 12 grams of benzene. There's the molar mass. And it's a sample going from -10 to 25 degrees. And look at all this information here, okay? So basically most of this problem is sifting through what we actually have to do. All right, so what I would encourage you is start with a diagram, okay? So you know you're going from -10 to 25 degrees, but this is benzene. You've never used it before. Probably you never don't know the specifics. So if we look here, benzene has a melting point of 5.5 degrees and it has a boiling point of 80 degrees. Well, we're not at 80, so we're not going to use the boiling point. And we're going to go through, -10 to 25 goes through this 5.5. So what I would recommend is making a curve. So I'm starting at -10. And I'm going to go on that curve up to 5.5, and then it's a phase change, so it's flat. Okay, so this is 5.5, this is still 5.5, and then it changes phases, and then it heats up some more, and that gets to 25 degrees Celsius. Okay, so in this example, we've got 3 problems. We've got Q equals MC delta T here, we got phase change here, and Q equals MC delta T here. Okay, so I just want to put up the framework for it, and I'll put up the answer, so if you have trouble getting it, then you can come see me and we can talk about it. But the first one is QMC delta T, so I'll label this number 1 here. So that's heat 1. And all the masses are going to be the same. So that's 12 grams. So you got mass. And this is a C. Well, if you go over here, wait a minute. This is the melting point. That means this is the solid and this is the liquid. So we need the specific heat of the solid to go here. And then you can see our temperature change is the -10. So that's our 5.5 minus our -10. That's the temperature change. So we've got mass, specific heat, delta T. So you've got Q. What I want to emphasize is that this Q turns out in joules. Let's see, while we're doing Q equals MC delta T, let's go ahead and do the third one here. Kind of in a groove with Q equals MC delta T, so we stick with that. So we're calling this region 3. Region 2 we're going to skip for now. So in this case, mass, we have the same, 12 grams. The C is the specific heat of the liquid because we changed into the liquid. So that goes here. And then the delta T is a different delta T. That's our 25 minus the 5.5. So T final minus T initial. Okay, so QMC delta T times 2, and those, again, give you both numbers in joules. So I'm really emphasizing that because the last calculation, region 2, is the conversion from the solid to the liquid. So we have to know that's heat of fusion or heat of melting. So we take that number, 9.8, and look at the units. So here I've been emphasizing the joules. This one is actually in kilojoules per mole. We've been using mass. We can't use mass here. We got to take our 12 grams molar mass, get to moles, and then we can get to kilojoules. Well, what is actually being asked? What are we doing here? If you take a look, it wants the total heat. How much heat is needed to go from totally -10 to 25? So we just convert everything to kilojoules or everything to joules. Depends on if it's a multiple choice, what the units are, or if you're indicated. But you're looking for the total, so they just all have to be in the same units, and then add them up. That gets you your total. So I'll put this up here, 2.1 kilojoules, but I encourage you to work this out and then come see me during office hours if you want to go over it. So the last chapter that we're adding, so just a few slides here, and it starts out with some interesting stuff. So still looking at different states, and a phase diagram shows a map of the states. So what pressure, what temperature does the state exist? Okay, so this is what a phase diagram is. And if you take a look here right away, you can see it's pretty unique looking, but I want you to see this is pressure on the y-axis, temperature on the x-axis. And I want to point out several regions. So the top left is going to be where the solid is. You move to the right, that's where the liquid is. And then if you move to the bottom, that's where the gas is. And we can double check that, right? So high temperature, yeah, that separates particles into the gas phase. Low pressure, that's into the gas phase. High pressure makes it compact, solid. So these are the different areas, and I'm going to point out some other things. We've been talking about fusion. That's where you change. So I'm moving from solid section to the liquid section. Vaporization, we talked about that. That's going from the liquid to the gas section. And then we also talked about sublimation, going directly from the solid to the gas, or deposition going back from the gas. A couple of things that are unique that maybe you haven't heard about before or seen. The triple point is actually one point that exists. So if we go over here and say it's at this pressure, it's at this temperature, and that's where the water liquid, water solid, water gas all exist at equilibrium at one time. So that's really unique. And then we get up here to the critical point, and you can see the line stops. There's no separation between liquid and gas. This is called supercritical fluid. So we, have focused on for sure for a year in chemistry, states of matter are solid, liquid, gas. Now you're seeing this extra state we're talking about, supercritical fluid. What does that mean? Well, it's defined as the gas and liquid state commingle. It has properties of both. You can't distinguish and say, oh, there's the gas phase, there's the liquid phase. It's all one, okay? Supercritical fluid. So, of course, with high temperature, this is when this can happen. So I just want to do a couple more phase diagrams. This is still a phase diagram for water, and I pointed out the triple point, pointed out the fusion curve, and the sublimation curve, and the vaporization curve. So now I just want to show you the movement, okay? So if you talk about 1 atmosphere, that's atmospheric pressure. And you can see right here at 0 degrees Celsius, roughly, that's where the solid goes to the liquid, okay? And you can see right over here, 100 degrees Celsius, that's where the liquid goes to the gas. So that's movement of temperature change at one constant pressure. Then if we talk about room temperature, and we talk about a decrease in pressure, you can see how it moves from a liquid to a gas. So this is the movement of a phase diagram. This is how you can use these things. And all of them have the similar kind of framework. There's solid, liquid, gas. There's the triple point, and there's this critical point. And you can just be asked questions of what if it's moved at 1 atmosphere from this temperature to this temperature? What happens? Well, if it goes from a solid to a gas directly, that's sublimation. What's this point at this pressure and temperature? What's this point? So these are phase diagrams, kind of diagrams to understand what's existing or what changes would take place. All right, so we end with getting back to our solids. Mentioned the crystalline solids, so this is the repeating pattern over and over. And if you take a look, right now we've got 3 different types of solids. The categories are molecular, ionic, and atomic. So first on the left I want to talk about, these are different compounds, right? An ionic compound makes up ionic solids. Covalent compounds or molecular compounds make up molecular solids. So you know about these compounds. Well, then that helps us with this. So a crystalline of a molecular solid made up of molecules, and what holds these molecules together is intermolecular forces. And those are relatively weak, so these have low melting points. On the other hand, ionic solids are made up of charges, cations and anions, so that's really strong attraction. That's a bond. That's a high melting point. So table salt, things like that, really high melting point. So those are the compounds that we talked about, molecular and covalent. So number 3 is actually elements. So it's just made up of atoms, but there's 3 different types of those. So now we have another number set of 3, and we have non-bonding atoms, we have metallic atoms, and we have network covalent atoms. So low melting points is when there's no bonds, the atoms are just held together with dispersion. Remember, dispersion's the weakest, are noble gases, that's xenon here, weak interactions, low melting points. Metals, this is metallic bonding. We don't talk about this anywhere in our curriculum, but metals are really important. They have a unique way to bond. Their melting points actually vary. So some metals, you put it in your hand, it'll melt in your hand. Mercury is a liquid at room temperature. Some have really, really high melting points. So this varies. And then network covalent. So now there's actually bonds between these atoms. These are really high melting points. So that's quartz as an example of this. So really encourage you, look over, this is the last chapter. Come see me during office hours if you want to review it and get ready for that exam 4.